So, this type of situations are to be avoided, that I cannot take the output signals, output ports, I cannot read it. So, we cannot it cannot be read, so they can only be driven. So, outputs can only be driven. So, that actually is a good thing, because what happens is that if you are having a circuit like this, okay, and this is an output port. Now, you need to so suppose this point it goes to 10 different places in my circuit, in my whole design, that goes to 10 different places. So, what will be the delay of this line, or whether you need a driver here to be put or not, whether you need a driver here to be put or not. So, that depends about the number of fan outs. But if I say that this line is also coming inside, okay, then that calculation is becoming very difficult. So, I cannot find out this driver strength. So, if this is the block and this is the line going out. So, depending upon the load that you have here, so you can determine whether I need to put a driver here or not. But if you are taking this line back inside the circuit, then I cannot do that calculation. So, that is why these VHDL designers, so they have said that this is not a good design practice, and it should be it should not be allowed, it should be avoided. So, if we follow that paradigm, then we can modify the design like this. So, we can say that instead of x, so we take another signal xtemp or xtmp, and then we say that the process description becomes like this, that if s equal to 0, then xtemp equal to a, else xtemp equal to b, and if xtemp equal to 0 and s equal to 0, then we make y equal to 1, else y equal to 0, and finally, we transfer this xtemp value to x. So, that is a legal description. So, we can do this change. So, signals can only be defined in this place before the begin keyword. So, this is another restriction. So, it is defining like this, that I am defining a block. So, this is my architecture, okay, and within this architecture, at the very beginning I have to tell what are the signal lines I have. So, this xtemp is a new signal line that I am defining. So, this is the xtemp line, and whatever circuitry I have here after this. So, they may take input from xtemp, or they may drive this xtemp. For example, here, so this xtemp line is driven by A, here xtemp line is driven by B, or sometime later this x is copied, this xtemp is going to be connected to x here. So, that may be possible, but I cannot define this xtemp line inside the description of this process. So, you cannot take this signal line inside. So, that is not allowed, that is not allowed. So, signals can be defined can only be defined in this place before the begin keyword. So, before begin keyword I have to define all the signals. So, this is the general. So, now if you, as I said that this process ABS xtemp. So, now what I mean is that if you look into this particular description, you will see that whenever any of these values are changing, like if A value is changed, then this xtemp has to be recalculated. If B value is changed, then the xtemp has to be recalculated. Y value has to be recalculated, and x value has to be recalculated. So, any of these signal values changing, I need to recalculate this thing, recalculate the values of x and y. So, this is done by means of this sensitivity list. So, these signals that we are putting within bracket after the process keyword. So, they are called the sensitivity list for the process. So, they will include all signals in the sensitivity list of the process, which either appear in relational comparisons or on the right side of the assignment operator inside the process construct. So, you see, so this is the general rule. So, which appear in the relational comparison. So, whenever I am doing these comparisons, so this will be done, okay, or whenever it appears on the right side of this assignment A, B, etc. So, then also this is done. So, if you do not do this, then what will happen? So, this if for example, if I do not include S in this at this point, that means my design is not dependent on the value of S. So, it is not sensitive to the value of S. So, even if S changes, my design is expected not to change, but that is wrong, because in my description I see that I need to have this value when S value of S changes, there is a chance that so instead it was previously outputting A and now it should output B. So, the value of X temp has to change, as a result X has to change. So, it is not correct. So, any signal that on which this description is going to depend, so those names must be appearing in this sensitivity list, otherwise there is problem. So, we cannot the description is not correct. Okay. So, that is the point of sensitivity list. So, in our example, this X temp S and S, they occur in relational comparison. A, B and X temp occur on the right side of the assignment operators. So, they are all part of the this symbol. So, that was the sequential description. So, I was describing the behavior of I was defining the behavior of the process in terms of my circuit in terms of a sequential statement. So, first it will execute this statement, then it will execute this if statement, then it will execute this statement. There are three main statements that we have. So, they will be executed one after the other. However, there can be another style of description which is known as concurrent description. So, and this is more close to the hardware, because we know that in hardware everything is in parallel in nature. So, this as far as the hardware description is concerned, so it is written like this. So, again this has to be architecture. This is another architecture of this my circuit. So, you see the entity name remains same. However, name of the architecture changes. So, behave concurrent. So, this is the name given, and here also the signal is defined. So, signal is defined as this one X temp, and then I am writing a set of concurrent statements. So, this is one first concurrent statement, this is the second concurrent statement, this is the third concurrent statement. So, these three concurrent statements, so they are put one after the other. So, and they are as if they are three parallel piece of hardware. So, all of them are executing in parallel. So, this X temp getting A when S equal to 0 else B. So, it is it will be taken like this. So, this S is there and this is 0 and 1. So, if S equal to 0, so this is A and otherwise this is B. So, this is the line X temp. Now, second line says that y is 1 when X temp equal to 0 and S equal to 0. So, this is my y. So, this is another multiplexer, X temp equal to 0 and S equal to 0. So, both of them being 0. So, that is your NOR gate. So, this X temp and y and X temp and S, they will be coming there, and so this is both of them being 0. Sorry, this is if both of them are 0, then it should be 1. So, this I need to this should be an OR gate. This is not an OR gate, this is an OR gate. Both the inputs are 0, then this is equal to 1. This is wrong, sorry. So, this is the first part, this is my S is the select line and this is A and B. When S equal to 0, then A. So, this is my X temp, and this X temp and S, so they are to be connected to form the input to the select input of the mux. So, this is 0 and 1. And 0 will be selected when this is y is equal to 1 when X temp equal to 0 and this is y is S equal to also equal to 0. So, that is a NOR gate. If I put a NOR gate, X temp is connected here and S is connected here. So, both of them being 0, the output is 1, as a result this will be selected, otherwise this will be 0. So, this is your y, and then X equal to X temp. So, from this point, so it is going to X also. So, you see it is some sort of a circuit, you can at most tell okay there is a buffer here and it goes like this. So, you see that this is a type of circuit that you get. Now, all these modules, so they are parallel, they are working in parallel. So, there are 3 different statements and they are working in parallel. So, that is why it is a concurrent behavior of the same block. So, we can do this. So, this is also valid. So, somebody may describe the circuit from a sequential angle, somebody may describe the circuit from a concurrent angle, but both of them are correct. So, this way I can have several architectures for the same behavior. So far we have talked about signals. Sometimes we are using some variables also in our description. So, normally when we are writing a sequential description in our programming software programming languages, we are more familiar with variables, not with signals. But in case of VHDL, we have got 2 types of temporaries, some of them are called signals, some of them are called variables. So, signals are the temporaries for which there are dedicated signal lines or wires that will be there in the system. So, as a result there will be some delay associated with the value assigned to a signal, like if I have got a signal line like this. So, this side is say x and this side is say y, and if I say y gets the value of x, then there is a certain delay associated with this. So, this value of x cannot come to y immediately. So, it takes some time, whereas other type of temporary, if this x and y they happen to be variable, and if I say y equal to x, y assigned to x, and this assignment is immediate because it is just, you can say it is another name of that variable. So, even if I do not use a new variable y, so I can take the value x directly and use it, but just for the sake of simplicity in my writing. So, I am using a new variable name. So, these signals are they follow the notion of event scheduling. So, once an event is characterized by a time value pair. So, this x equal to x temp means schedule the assignment of the value of signal x temp to signal x at current time plus delta. So, this x has got the this x temp value will be coming to x, that it is scheduled at current time plus delta, some time will be spent. So, this may be infinitesimally small time amount used by the simulator for processing the signals, but it is not immediate. Like if there are the 2 places, so if there is one place which is generating this x temp, so this block is executing this statement x, and this x is used by another block, then you see that when this x has got the value of this x temp, so it is not available immediately. So, as far as this block is concerned, so this will see the old value of x for some very small amount of time. So, that actually helps in the simulation process. Otherwise, if that was not there, then the simulation will not terminate. So, it will go on doing the thing again and again. So, because it will be always getting a new value of x temp, as a result it will be going into an infinite loop. Just to avoid that, the simulator designers, they have said that this x signal assignment, like x assign the value x temp. So, this will schedule the assignment to take place after time delta, after the current time, after some delta time unit, where this delta is infinitesimally small amount of time. So, this is there is no hard and fast rule like how small it should be, it is determined by the simulator designer. On the other hand, variables, they do not have the notion of events, and variables can be defined and used only within the process block. So, only within process you can define a variable, and variable declaration and assignment. So, it is done like this. So, this variable k bit, so the begin, so assign value, so k assigned as L. So, this k assigned as L, so k is a variable, so it gets the value of L. So, it gets it immediately. So, this L is a signal, so k gets the value of L immediately, but if it had been a signal assignment, then it will take some infinitesimal small amount of time for doing the assignment. So, we have got these signals and variables implemented. So, they are 2 different types of notions that we have in VHDL. So, signals means there are say physical wires which will be connecting, as a result there will be delays and all, but for variables, so it is immediate. So, it is just a shorthand for some complex expression. So, that is done here. So, variable can only be defined and used inside the process construct. So, signals can be defined in any architecture before the begin statement, but these signals, these variables, they can be defined only within the process. So, they cannot be defined outside the process. So, how do we simulate a circuit? So, simulation is the modeling of the output response of a circuit to a given stimuli. So, we have got these values of A, B and S. We need to determine the values of X and Y. There are many types of simulators that are available. One is called event driven simulator. So, that is most popular. So, this event driven simulator is this is when some event occurs, on the simulation on the lines A, B and S. So, this circuit will be simulated and we will get the outputs X and Y. So, Model Sim is a very popular simulation tool that is available. It is also available freely for download. So, you can check it and you can use it for your simulation. So, how does it simulate? So, if this is the description that I have, now at time t 0 minus. So, 0 minus means just before starting the simulation, the values of A, B and S, they are unknown, then the value of x temp is undefined, value of y is undefined, x temp variable is also undefined, and x, the variable, the signal x is also undefined. So, this is the condition just before starting the simulation. So, at time 0, if I say that I have applied a pattern 0 1 0 in A, B, S at time 0 and simulation starts at this time, then at time 0, so this is the situation. So, 0 1 0 and this x temp is getting, so this this evaluation is done. So, x temp will be assigned the value A, but after an infinite after a small amount of delay. So, as a result, this x temp y, x temp var and x, they continue to hold the value x. Then after some small delay d, these assignments will take place. As a result, this x temp gets the value, since s equal to 0, x temp gets the value of A. So, x temp becomes equal to 0. Similarly, x temp equal to 0 and s equal to 0. So, this y also gets the value 1. So, y is also getting the value. So, y sorry. So, at this time x temp is, so it actually while evaluating, so it takes the previous value of this x temp and that was equal to x. So, this condition was not satisfied. So, it got y equal to 0. So, you get y equal to 0 and this x temp var assigned to the value of x temp. So, x temp value was 0. So, that value is coming here, whereas x, the variable, the signal x, it continues to hold the previous value because this assignment has been scheduled, but this is with the value of x temp value. So, this old value is taken. So, it is using this, whereas this x temp var, since it is a variable assignment, it takes the value of x temp immediately and becomes 0 here, whereas x continues to be unknown. At 0 plus 2d, ABS remains unchanged. Now, this y becomes equal to 1 because now x temp value has become 0. So, y becomes equal to 1. So, that is changed and then this x is getting the value x temp. So, x is getting the value 0. Now, at time 1, if we say that we change the input pattern set to 0 1 1, then this previous value of this thing they continue to hold, and it in a similar fashion the rest of the simulation is done. So, you can the whatever way we were describing here. So, it is done here also. So, at time 0, so scheduled events list. So, it has got x temp will be assigned 0 at time 0 plus d, y will be assigned 0 at time 0 plus d, x will be assigned x at time 0 plus d. So, that is the scheduled event. So, after and but the variable assignment is executed, this x temp var equal to x. So, that is executed. Now, at this next time at 0 plus d, so these are the scheduled events executed, x temp becomes equal to 0, y equal to 0 and x equal to x, assignment executed, x temp var equal to 0, and these are the scheduled events. So, x temp equal to x 0 plus 0 at 0 plus 2d, y equal to 1 at 0 plus 2d. So, these are the scheduled events, that is at this time. So, these values should be assigned to the variables and signals. Next at 0 plus 2D, so this is the situation. So, these assignments are to be, this is a scheduled list of events and there is the scheduled events have been executed and there is no further scheduled event because this A, B, S, X temp. So, they have not changed their values, as a result no further simulation will be required. However, at the next time, at time 1, when this schedule will be taking place, this ABS value changes, then again the simulation will take place. Now, as far as the synthesis is concerned, so synthesis is the process of converting a behavioral description to structural level netlist. The abstract behavioral description maps to concrete logic level implementation. So, from the description, so it is converted into physical implementation. So, integers at behavioral level you might have defined something as integer, they will be mapped to bits at the structural level. So, that gives rise to a structural level netlist. So, so it will be in terms of logic elements, connections between them and all. So, that will give us a structural level netlist. Implementation of so structural level netlist is nothing but an implementation of behavioral description. So, it describes interconnection of gates, how these gates are interconnected and all. And there are large number of CAD tools. So, there are CAD design companies that have come up with CAD tools for doing this conversion from behavioral level to the structural level. So, that helps when you have got this complex design. So, that is going to help you. So, let us see how the structural level netlist is derived. So, coming back to our behavior. So, it was like this, when x equal to 0, x equal to a, x equal to 1, x equal to b, and then this output was when x equal to 0. So, this was the description. So, logic functions that are associated with it is, we say that s bar. So, this is calculated as not of s, x bar is not of x. So, x is defined as a and s bar or b and s, and y is defined as x bar and s bar. So, these are the logic functions for this behavioral description. So, that can be derived, and once we have derived that, so we can write down the corresponding structural level description. So, you see that this is another description, and then we can have the we can define some components, and then we can use those components onto this. So, here this component, in this case we do not need to define separately, because this not and or, so they are available as library modules in the in most of the VHDL synthesizers. So, we do not define these component declarations separately, but we define the signal lines S bar, W bar, S bar, X bar, W1, W2, they are of type bit. Now, next what we say is that G1, next we take help of these statements like G1 port map, it is a NOT gate, port map S bar S. So, it means that I have got an inverter whose name is G1 in one side. So, so it has got S as input and S bar as output. So, this S bar as output. So, this is the gate G1. G2 is an AND gate. So, that has got a port map of so AND gate has got one output and two input. So, this is fed to an AND gate. This AND gate is named G2, and in G2, so I have got this S bar line connected here, the A line comes here, and this output is W1. Similarly, I have got G3 as another AND gate. So, G3 is another AND gate, where I have got W2 as the output, and we have got this B and S as two inputs, B and S as two input. And then it says that G4 is another OR gate. So, G4 is another OR gate, and in this OR gate I have got X as the output, and this W1 and W2, they are the two inputs. So, this W1 and W2, they happen to be two input. And then G5 is a NOT gate or inverter. So, this G5 is a NOT gate, this is G5, where output is x bar. And finally, we have got G6 which is an AND gate. This G6 is an AND gate where we have got this y x bar as one input, s bar as another input. So, this is the s bar and we have got y as the output. So, this is the final circuit that we get. So, okay. So, this circuit realizes the same functionality that we have described previously, and you see that the same description. So, I am writing in terms of circuit components. Okay. So, I have done the design myself. So, I have done the design in terms of some logic gates, and then I am describing the circuit behavior in terms of those logic gates. So, I have say so it says that I have, so these are the components that I need: NOT gate, AND gate, OR gate. So, these are the three types of components we need. So, in this component declarations part, so you can define those components, but here it is not necessary, as I said that they are part of VHDL library. So, then I have to say how the ports are mapped, like say an inverter. So, it has got this NOT. So, this is the NOT component, and it has got inverter. So, it has got this output comma input. So, this output is mapped to S bar and input is mapped to S. Okay. So, that way this component is instantiated. So, this is called, these are called component instantiation. So, that way can be done. So, then so this similarly this AND gate. So, this is another one, G2 is one instance of AND gate, and then the port mapping is like this. G3 is another instance of AND gate, and this is the port mapping. So, this way we have we can describe the whole circuit in terms of these components and their connections. Now, so these are some of the further references for this VHDL. So, whatever we have done, so this is just a very preliminary description of this VHDL language. So, that is just the start point. So, I wanted to give you a feel like how can we describe the circuits and systems using VHDL language. So, it is a very vast language, and there are very good simulators available. So, you can download those simulators and you can refer to some of these mini reference and tutorial. So, they are very good. So, you can look into them for getting further reference for that, and textbooks are also available. So, you can go through that for digital design.